there it goes. Okay, so it looks like it's streaming now. So last time we left off. Where were we? We were right here. Whoops. We were right here. We talked about a simple one-dimensional physics problem where there was acceleration, and we discovered the importance of drawing an FBD, which is a free body diagram, not a force body diagram, although I don't really care about that. And we talked about how important it is to worry about the directions and the plus minus signs, the directions of the coordinate systems and the plus minus signs. So now we're going to do the logical thing and add in sines and cosines with vectors. So that's and this is on page 85 in the workbook, 85. Okay. Come on, Zoom. Oh my gosh. Hold on. Zoom's giving me grief. There we go. Okay, so now I want to start here at 5.6. And I'm probably going to do 5.6, 5.7, and maybe the next page. So I'm going to do these with you just because these are important problems for learning the idiosyncrasies of getting arrows right with angles and the names of the forces right. So let's start with 5.6. Just kind of skim over that one. All right. I'm going to get the board ready. Oops. What happened there? So I'm just going to try and draw this thing, and then we'll talk about it. So if you can, try to get as far as you can on parts A and B while I have to draw this thing. Or get, the idea is you're trying to draw on your page while I draw on my page here. Actually, for this one, maybe I got to leave that up there. Sorry. Oops. And then I'm just going to check something in the solution really quick. I forgot which colors I used. I think I used green for T1 and blue for T2 if you care. That doesn't matter, but I'm going to, oh, come on, marker. Okay, that one's dead. There we go. All right, so now I think I could share here. Oops, escape, stop the share. Okay, so you've had a second to look at that one. Whoops. There we go. And so, sorry, I ended up drawing the whole thing, and then I realized, wait a minute, this one's color-coded. It took me a minute to remember that. So hopefully, and again, this is 5.6. All right. So hopefully you've got a picture that maybe looks something like this. You don't need the color code. You could draw it all black and white. But the idea is there's a force vector here, a force vector that way, and this force vector down. Part A, now remember, these are all three strings that are pulling on the washer, okay? Now, in this case, under what circumstances is this string tension equal to the weight that's hanging down here? So if you recall, there was a little weight that was hanging on here like this. Under what circumstances is this tension equal to this weight, mg, that weight magnitude? What do you think? Somebody.
If the j hats of T1 and T2 add up to equal the mass?
Nope. Think back to questions 5.3 and 4. Take a look at 5.3 and 5.4 at the top. Do you remember, when does the tension equal the true weight? When an elevator was moving up and down versus accelerating up and down, one of those situations caused the tension not to equal mg. Do you remember from last time? Oh, maybe there's one in the chat. Somebody may have said it. Yes, Edgar got it. Thank you, Edgar. Sorry it took me so long to notice that if you had said that a while back. So remember, if A equals 0, this tension will equal the true weight. So basically, as long as you don't put this thing in an elevator or on a rocket ship or something where it's going left and right and accelerating, or up and down and accelerating, we'd expect this to be true. And actually, left-right shouldn't affect the vertical at all, right? So actually, yeah, it does. And we'll get to that in chapter 6, I think, maybe in Physics 161. But anyways, yeah, as long as acceleration is equal to 0, and I'll put a vector on there, that's true. All right, and so this is true. We're not in an elevator for this problem. Okay, so now I've drawn the picture of the washer with the forces acting on it. So this is the FBD. And to be clear, I'm doing an FBD for the washer. Now, it may help us to split this into components. So maybe to do that, I might move this T1 over to here. So let's look at this one. I could split this thing up into some force sideways and some force up and down. That will relate to this angle phi. So let's get back to your old school geometry days. I don't know if you could see it or not. There's a lot of geometry in physics. So right here and right here, those are two parallel lines, and this is going to be the same angle right here and right here. Do you see that? Alternate whatevers. Technical term, alternate whatevers. Okay. Now let's do the same thing over here and see if we can analyze it. This one, I just want to point out that this angle and this angle are parallel. So this would be theta, not that. That's, we got to watch out for. So does everybody understand why here I was going horizontal to horizontal? That's why this angle is phi and phi. But over here, I'm comparing this line to this line, and that's why this is phi and this is phi. Right? So here they were vertical parallel lines. Here they were horizontal. All right. So somebody help me out. I'm going to ask you about these components. So it's either going to be T1 cosine phi or T1 sine phi, and similarly T2 cosine or T2 sine. So let's look at this one. Should this be a T1 cosine or a T1 sine right here?
T1 cosine?
T1 cosine. Now remember, phi and theta are not different. So this is phi because it's got that kind of vertical line, nearly vertical line. Well, I could tell already this one must be T1 sine phi, right? So now let's go over to here. Somebody else, what's this one? T2 cos or T2 sine of theta?
Sine.
Exactly, opposite. And so you could see that in physics, sometimes they give you angles to the vertical, which flips your standard. Well, see, look, I started writing it too. You have this habit of always wanting to say cosine for the x direction. Just be careful for that. That makes this one T2 cosine. And now before I write down any equations, sometimes I double check that just to make sure. Opposite is sine, adjacent, because it would really stink to screw up at this stage and not double check it and then do all the work and have to be like, oh, I got to start all over. It's not the end of the world, but just double check. Adjacent gets the cosine, adjacent gets the cosine. Feeling good. All right. So now let's see where we're at in the question. Maybe. Write the force equations in the x and y directions. Now, I know you have the answers, so if I'm too slow, write it down and just work ahead, right? And just keep doing problems if I'm too slow for you. But if I'm not too slow, then I'll just try and work and then hide it from you. So I'm going to write down what I think, and you write down what you think, okay? We're trying to get the force equations. And in particular, this problem had acceleration equals 0. So maybe somewhere I'm going to sneak that in here. Just because I had to squeeze that in somewhere. I'm just going to mention I'm using a standard coordinate system where x is to the right, y is up, and the acceleration is 0. Remember your equations. They are sum of force in the x is mass acceleration in the x. This stuff comes from the arrows. This stuff comes from right there. And then you got the same type of equation in the y direction. Again, this, the sum of forces in the y, sorry, there's glare. The sum of forces in the y comes from the vertical arrows in the picture. And this comes from acceleration up there. Notice I did not draw acceleration touching the washer. Okay, it's not a force. Okay, see what you get. I'll write down what I get. Okay. That glare is pretty bad today, huh? All right. So this is what I got here. I don't know if you can see that. All right. So let's walk through this one. I had a negative T1 cos phi. That's this one. It's negative because arrow goes to the left. I have a plus, plus T2 sine. That one's going to the right. And then in this case, acceleration is 0, both x and y. So I know that this side is 0 if a is 0. So any questions about the sum of forces in the x? The sum of forces comes from the left-right arrows. The 0 comes from the acceleration. Going over here to this one, I get a plus T1 sine phi. That's going plus, because it's going up in the y, T1 sine phi. T2 cos, that one's going up. And then T3 is down. You may have written mg. That's also fine. Because do you agree that T3, the magnitude of this tension, is equal to the magnitude of the weight because this thing's not accelerating? So it's okay in this special case to just switch T3 with mg. And then again, it equals 0. So I'm going to pause and see if this is making any sense or any questions you want. Remember, you could also ask Jay as well. You can keep chatting with Jay. And you've got the solutions too. If you learn better from the solutions than waiting on me. All right. Hopefully this is feeling okay. Let's see what the next thing is. On the question, it says, I'm just reading it here. Okay. Oh, all right. So parts D and E. Parts D and E are going to show you two classic physics math techniques you need to know. So we're going to use parts D and parts E over and over and over again. The two things that are very common to solve for in a physics problem are this, right? It's like, which direction should the force go so that this thing doesn't fall apart? That's a reasonable question. So that would be solving for the angle. I believe that's asked in part D, right? And then the other thing is, how much tension is going to be in this string? If I know how much tension will be in the string, that gives me an idea what size string I need to use so this thing doesn't fall apart, right? So if I need to hold up 70 pounds, man, I'd better not use a line that's only rated to 10 pounds, that kind of thing. So we usually need to know either one of these tensions or one of these angles. Sometimes you need to know the mass, etc. So let's do this. And just to save some time, I want to show you this. Well, actually, the first one, let's try and do this without the solutions for just a second. Any ideas how you would get rid of, we're trying to solve for, what was it? Theta. So basically, let's do this. Let's assume T2 and theta are unknown. And what we want to do, if these two things are unknown, we want to find ways to manipulate them to solve for either the angle or T2. So let's start with the angle. Does anybody have an idea what you would try? Just unmute or throw it in the chat. How would you solve this gunk for theta? Assume T1 is known, phi is known, T3 is known. So basically, only the blue stuff is unknown. Only the blue stuff is unknown. Two equations, two unknowns. It's slightly sneaky, isn't it? The classic thing some student usually says if we're in the classroom is they immediately say, oh, well, I'll just solve for T2 in this equation and plug it in. Well, that's doable, but that gets pretty complicated because then you've got sine theta and cosine theta in the same equation multiplied by each other. Ugh. It's not very pleasant. So let me show you the trick, and I have it written up here. And so I know it's kind of weird trying to be involved in this class, but so this is what I would do right here. Set up these equations so you get T2 times sine theta on one side and T2 times cosine theta on the other side. And then what you do is you take a ratio. So literally you divide, you just take this equation right here and you just divide them out. When you do that, the T2 drops out and you get sine theta over cosine theta, which is tangent theta. And that's the trick. It just saves you a lot of time. So I often say, what would Horatio do? Horatio would take a ratio. And so notice all this stuff on the other side, you just leave it alone and it's just ugly, but it's done. So rather than work that hard, so let's see what that looks like live, okay? So in this case, what you could do, I isolate this one. And I isolate that one. So the idea is we want it to look like this so that we could take the ratio and get rid of T2 really quickly. So if I do that to this first equation, all I have to do is move this one to the other side. Ding. That's T1 cosine phi. Now over here, what I have to do is I have to move both of these to the other side. T3 is going to move to the other side and be positive. This one will be negative. So, and because T3 happens to equal mg in this case, when I move that over, I get mg minus T1 sine of phi. At this point, you divide them out. When you do that, T2 drops out. Sine theta over cosine theta is tangent theta. Like this. And over here on this side, watch out. Okay. So a lot of people say, well, wait, can't I just divide through by cosine theta and get a tangent phi on this side? Well, this term doesn't have any crap. Whatever you do to one term in either the numerator or the denominator, you have to do to all terms. Otherwise, you're changing the equation. So you could divide by cosine phi. It would drop out here. It would make this a tangent, but then this would become mg over cosine phi. So basically, there's not much you can do over here to clean it up. So let's just leave it. So that's how we get that. And then obviously you could take inverse tangent of both sides. If you want to get the angle, take tangent inverse of this, and that drops out. Okay, so that's how you could get the angle, theta. We see that you got to be careful all the way down with this whole problem. Look, you got to be careful with your plus minus signs and your angles. Many problems have more than one angle. So a lot of problems use theta and phi. Some of them use angles alpha, beta, gamma, but yeah, those are the most common angles you're going to see in a physics class: alpha, beta, gamma, delta, and phi and theta. So just watch your angles, watch your signs. All right. Now here comes another fun one. What if instead I wanted to solve for T2? The common thing students usually say is, I'm going to just take this equation, move everything to the other side. Well, that's what we did right here. So this is now, if I wanted to find the angle, which is the other part, which was part E, we just finished part D. A lot of students say, well, shoot, why don't we just move this T2 over to here, take sine inverse of this, get the angle, then plug that into there, and then try and solve for T2 with a cosine of a sine inverse with the T2 inside. Ugh, that's horrible, horrible. The trick to solving for t, if theta is unknown, is this. Remember this. Grab each equation and square both sides. Now, if you do it to one side, you've got to do it to the other. And notice you can't just square each term. You have to square that whole pile of crap. Why is that useful? Well, if I square these things and add them together, notice, let's see what happens here. If you square these, isn't this T2 sine squared? T2 squared. Cosine squared. Well, that's the same thing as T2 squared times the quantity sine squared plus cosine squared theta. What's this equal to? What's sine squared plus cosine squared always equal to?
1.
1. And so notice that gets rid of the angles without having to do sine inverse, cosine inverse there. So this side just becomes T2 squared. That's a lot easier. Now I'll show you in the solutions just so you can get a feeling. And there was some chat there. My bad if I missed it. Yeah, good job. And so this is what I was trying to show you there. This part, whoops. This thing goes to 1. And then you get tension 2 is plus or minus. Well, it's going to be plus because it's a magnitude. You get this big ugly mess. And that's fine. That's valid. And then you might be saying, could I try and clean this up a little bit? You could, to be honest, you could FOIL this out. And I think what you end up getting is T1 squared plus mg squared minus 2 mg T1 sine phi. And notice that looks a lot like the law of cosines, but not exactly the same. Because when you FOIL this out, the T1 squared plus the T cosine squared becomes this. You've got the mg squared here, but you also have the cross term. The cross term gives you this crap. So if you're curious, that's some different ways. All right. Now, I know that's just math, but let's face it. You're going to have to do a lot of these problems. There's times you need to do some math, and that's what this class is about, is getting you ready. So just remember that trick. So the goal of this problem was to show you, 1, split up forces with left and right arrows. Use that to get plus minus signs in the force equations. 2, watch out for angles to the vertical. That flips the standard thought process on sine and cosine, right? If your angle is to the vertical, the x component has sine theta and the y component has cosine theta. So there's 2 things. 3rd, if acceleration equals 0, this tension was equal to the weight hanging on it. That was good. And then the 3rd and 4th things were basically, remember the tricks, the 2 math tricks we saw. You can either square the equations and add them together, which eliminates the angle, or you can isolate the equations and take a ratio, which eliminates the magnitude out front. All right. That was that question. All right. We've got 10 minutes here. Let's take a look. Any questions? Any questions on any of that? I'll pause. All right. So let's go back and look at this one. Let's look at the next one. It's a subtle variation, but I discovered if we don't take the time to do 5.7, I see lots of mistakes on test day. So clearly 5.7 is worth doing, okay? So let's look at 5.7. And so now I think you could do this. Try to draw a hanging FBD of the mass. So read that question, you draw it, I'm going to draw it as well. Okay. So we've got, oh, that's very faint. Draw that a little bit better here. So now the idea is you take a mass and you hang it on here. I didn't plan very well. I don't have a big hanging mass. I bet I could do it with this. Give me a second here. So here you go. Suppose your students keep failing your quizzes and you just are driven to drinking, but instead decide to hang that from a rubber band. That would be this physics problem. Okay. Or maybe you're the student and you're tired of your instructor giving you quizzes that fails you. That's more likely. All right. So I'm going to try and do this here. That's supposed to be an image of this thing. And if I do this right, notice the angles are about the same. I don't know if you can see that, but so obviously the more I stretch it, this is actually a pretty good demonstration of this, believe it or not. So what force is holding up this giant flask? Is it a normal force or is it a tension?
Tension?
Tension. And that's the thing. You know that this rubber band has tension in it, right? So that's, and sometimes students will say, well, it's sitting on top of the rubber band. Isn't that a normal force? And to be honest, I could say, okay, I could see why you would say that. But in practice, what I want you to get in the habit of doing is thinking of this is a tension going this way. And then if it's symmetrical, I hope you agree it should be the same tension going this way. Do you agree? Gosh, what happened? This blue was working so great a minute ago. Maybe I was using this other blue. Aha! I got the blues. All right, there we go. So now this is, hopefully this makes sense. Think about it. If I have the same angle, if the tensions were different, wouldn't that cause different horizontal components? I'm going to get this one out of here before I forget. So the idea here is the tension horizontally needs to be the same. Otherwise, this thing wouldn't be balanced. Well, I was just looking at it. I could see from hanging it here, it's balanced left and right. It's not accelerating left or right. Okay. So now I know this tension and that tension are the same. If this angle's phi, this would be phi. This side should be t what? Cosine or t sine of phi?
Cosine?
Looks good. It's adjacent. And that's t sine up there. So now in this case, there is no normal force. We've already accounted for the rubber band. The rubber band or the string or whatever was giving tension force, and it's that tension force that was holding it up. So what I'm saying here is do not do this. Some students will add in a normal force there. That's not right. I could see why you would think that because it is setting on the surface of the rubber band, but it's the tension in the rubber band that's holding it up. All right. And the left-right tension in the rubber band gets canceled. So the vertical component of the tension is what's holding it up. And in fact, I don't know if you see this, but what are the sum of forces in the y direction? That's going to equal mass times acceleration in the y. If this thing is hanging here like this, what's the acceleration in the y direction right now?
0.
0. So now, what are the forces upwards in this case? Somebody give me one.
Is it 0 also?
Oh, that's true. But what is one of the forces? They add up to 0, but there's different forces. So what's one of the forces in the vertical direction? Remember, this came from the acceleration. These come from the arrows up and down. Give me one arrow that's going up or down and tell me the force magnitude associated with that arrow. t sine theta. That's where I was going. Did that make sense? And since there's one here and one over here, there's actually two of those. Are there any other forces acting on this mass?
Force of gravity, mg.
Yep, mg. So there's an mg downwards, right? And all that should equal 0. Okay. So far, so good. So from this, let's solve this for the tension. I move this over, I divide by 2 sine theta. So again, I move the mg over, I divide by the 2 sine theta, 2 sine theta. Okay. Does that make sense?
Yes.
Okay. In what sense? Why does that make sense to you? What's one way you could check this? I could say it that way. What's one thing we could check about this? Check the
units.
Nice. What are the units? Well, I have a kilogram times a meter per second squared. And then I'm going to divide this by, what are the units of 2?
None.
What are the units of a function?
None.
So it's kilogram meter per second. That's a Newton. That's a force. Looking good. What about the angle? What's a simple number you could plug in for the angle, and what would that look like? So what's the easiest number to plug into any formula?
0.
0. What would this look like if theta was equal to 0? If theta was equal to 0, what would the strings look like? Would they be horizontal or vertical?
They'd be horizontal.
Would they? This angle, let's see. Oh, shoot. That's a tricky one. Let's do an easier one. Okay, what's the other easy angle then? You're right. So I just know that physically it's impossible for me to do 0. So what's the next easiest number? How about 90? Do you agree that 90 would be straight up and down?
Yeah.
Nice job. Nice job. So that would look like this, right? Now think, if you hang this straight up and down, shouldn't each one of these support half the weight? Well, think. What's sine of 90?
0. Wait,
One.
1.
So, and that notice that the tension is exactly half the weight when you go straight up and down. So now let's see why I got freaked out by plugging in 0. What is sine of 0 degrees?
That's 0.
So what's mg over 0?
Undefined.
Okay, let's see. Now think about this. What we see is the closer the arrow gets to 0, the more tension you have. Now think about this. Look at the angle, and I'll try and get my shirt, which allows you to see the rubber band here. So as I pull this out, obviously at some point this is going to smash and not only hurt me, but drop on my toes. So I probably will not go too much farther. It's not perfectly frictionless, but you can see I'm putting pretty intense tension on this to get a small angle. And so this is like a rock climber's dilemma. If you're going to climb rocks, you basically don't want your angles to get much bigger than that. Why? If you fall down, there's already a whole bunch of tension on your ropes. In this case, if you fall down and add more tension, the rope snaps and you're dead. Or what if you're hanging a sign? While this might look cool, what if a gust of wind comes up? A gust of wind would add extra tension and might break the sign. So generally speaking, you probably want to hang things with the angles close to 90 degrees from the vertical, or well, depending which. Basically, you want the strings to be close to up and down. That way, the string tension is only close to half the weight. The more angle you have, the more trouble you have. Think about braces on your teeth. I know it's time to go, but this is, we'll pick up here next time. But imagine you have teeth that are crooked. And I'm going to do an aerial view of these teeth. So apologies if this is ugly. This is supposed to be a view from above of some teeth. So, right, you're looking down and here's the teeth and they go around all the way. So this is supposed to be your smile and we're looking down on the teeth from that angle, okay? So obviously braces, you put these brackets on here and then you put a wire on here. Look at that. If this tooth is out of whack, you're basically doing a force vector like this and a force vector like that. And as a result, you get a tiny force pushing the tooth back into alignment. That means you need extremely high tension on these wires on your mouth, which is painful as a kid or an adult with braces. So, right, they have to crank up the tension to get any significant component of force pushing the tooth into alignment. And so, yeah, or let's go this way. This is you could play this in reverse. Check this out. Your car is stuck in the mud. Okay, let's say this is an aerial view of your car. Your car is stuck in the mud and you want to get it out. So one thing you could do is you could take a rope and run it over here to a tree. All right. And then if you push sideways on the rope, you add a lot of tension and can pull your car forwards a few inches very easily. Right. But then you have to shorten the rope and then you push in the middle. But if you push in the middle with a small force, you get this massive tension due to the small angles that could actually pull your car out. Or if you aren't thinking, it could rip your bumper off. Let's call that good. So make sure you're careful with your knots, etc.